All right, good morning. Again, my name is Andrew Farrington, and this is the second lecture on Aspen one-liner. We're going to go over how to model the remaining equipment and probably leave off right before we start running faults. So we left off with modeling three winding transformers. This is very similar, although there are some differences between three winding transformers and two winding transformers. But it's very similar primarily with two winding transformers. I'm just going to cover the differences here. So with three winding transformers, there's obviously three windings. They're referred to as the primary, secondary, and tertiary windings. Your particular transformer may call them primary winding and then two secondary windings, but in one-liner, they call it primary, secondary, and tertiary, which is generally what they're called by the manufacturers as well. The So for your impedances, therefore, you're going to have an impedance for positive sequence impedance for the primary to secondary winding, the primary to the tertiary winding, and then the secondary to the tertiary winding. So you have to enter each of those individually. And then the zero sequence impedance is also in a similar manner from primary to secondary, from primary to tertiary, and secondary to tertiary windings. So you'll have to enter each of those individually. Generally, you're given that data in the test report in a similar manner as the two winding transformer, but they give you each of those values separately. So you have the primary to tertiary impedance, the primary to secondary impedance, and then the secondary to tertiary impedance. These are the zero sequence, but you'll have something similar for the positive sequence values. So you get each of those values, you can put them in here. Again, you've got the MVA base that you can change, whether you want to model it on 100 MVA or the transformer base rating, which is what I usually do. You've got different winding selections for three winding transformers. So this one happens to be an auto transformer with a delta tertiary, but you can also do, Y delta delta or YY with a Y tertiary or YY with a delta tertiary, etc. So you just pick your winding configuration and then model your impedances. With the zero sequence impedance, you've got the short circuit impedances, which kind of mimic the way that the positive sequence values are input, but there's also this classical T model impedance. I generally see this with older transformers. They used to, which is why I guess they call it the classical method, but they used to model the zero sequence impedance in this manner. This is the T method. Kind of looks like a T, that's why they call it that. And it models it with like this fictitious node here. Obviously, there's no node in the middle of the windings. You've got, the relationship between the primary and the tertiary and the primary and the secondary and tertiary. It's more of a delta, which is what these impedances use. But they used to give you this value or give you the values in this method. And so you can still input it that way if you have. And this particular transformer test report actually gave you both. They give you the primary, secondary, primary, tertiary, and secondary, tertiary impedances. And then they also give you the T diagram impedances. So you can put it in either way. The other thing to note about the zero sequence impedances for three winding transformers is if you don't have the zero sequence values for your three winding transformer, you can use this button that says estimate from the positive sequence parameters. So if you have the positive sequence parameters, you can just click that and it will give you typical zero sequence impedance parameters based on the positive sequence parameters. And you don't have that for the two winding transformer because in general you can assume for your transformer construction what the zero sequence impedance is. It's either equal to the positive sequence impedance or 90% of the positive sequence impedance, something like that. Again, that depends on the transformer construction, but in the three winding transformer, you can't just do 90% of these values, so you can estimate from the positive sequence parameters. So that's a cool button. The neutral impedance you put in the same way as the two-winding transformer. You've got the magnetizing susceptance. Again, that's generally very small. The magnetizing impedance is extremely high, so these can generally be assumed to be zero. And I think that's all I wanted to cover about the differences. I want to hammer the vector group again. So for a three-winding transformer, you've got kind of a longer abbreviated vector group name here. So this one's a YN, capital YN. That's the high voltage winding. So the capital Y means that the high voltage winding is a Y configuration. The N means that the neutral is available. Then you have a lowercase y and a lowercase n. That means the low voltage winding is also a Y with a neutral that's available. And then that has a offset or a phase shift of 0. So again, that clock method we talked about, these two windings are in phase with each other. And you can tell that graphically here by looking at the phasor diagram, or you can tell by the vector group abbreviation here. YN0 means that there's no phase shift. And then you also have a D1, so there's also a delta winding, and that lags the high voltage winding by 30 degrees. Again, clock method, we went over that last class. So that's what this represents. Let's see, phasing. Yeah, so again, you need to look at your phasing diagrams. You need to get the desired no load tap and LTC position. All of that same stuff applies for the tap KV. And you get it from the transformer. You get the data from the transformer nameplate and transformer test report. Now, touched briefly on this last class, but this is an example of how you would calculate your reactance if you're not given the reactance directly in the test report. Usually, you'll be given your load losses, and you can use the the reactance and resistance values. They might just give you the %Z, but you can calculate the R using the load losses and the transformer nameplate MVA rating that it was tested at, and then use that to get your R value, and then you can use trigonometry to obtain your X value, and then you can put the R and X values in the one-liner model. So you have a homework problem where you're not given that data. So this is an example of how to do it. So again, refer to this when you're looking at your homework problem. I don't want to go through this in depth, but let's see here. All right, modeling generators. So there's a few different types of generators that you can model in Aspen one-liner. They refer to the traditional synchronous generator as just a generator, and that's represented by this circle that doesn't have a number in it. Then there's also type 3, which are doubly fed induction machines, generally used for wind turbines. And then there's type 4 machines, again with a circle with a 4 in it. And those are like power electronics type generators, like inverters for battery energy storage systems or solar farms or whatnot. And we're going to go through each one of those in detail here. But the generator is a traditional induction generator. You model those by clicking on the bus, going to new generator, and then you get this generator data window. And if you have multiple generators connected to the same bus, you'll only model one generator using this method, but then you'll add the number of units that you have, and that's how they describe it. So you can't add more than one generator to a bus, what you do is you add one generator and then you add multiple units. The internal voltage source, you generally use one per unit because that's the voltage that it's putting out. And then the reference angle, we talked about this. This is important. It needs to be correct. Generally, you can just assume it's 0 and then do that check network anomalies function that we talked about last class to get the correct reference angle. Because depending on where your reference bus is, it might be challenging to try and determine what the appropriate reference angle is. So make sure you set that correctly because it'll screw up your fault current values when you use the linear network solution option, which we'll talk about at the beginning of next class. Current limits. These are generally not required for induction machines. These current limits were put in to kind of mimic the way that inverter or doubly fed induction machines were modeled prior to 2021 when they added type 3 and type 4 machines. So this was the way that Aspen provided guidance to mimic that operation. So current limit A, you might put in as your your immediate fault current. They would say put in a low impedance for the generator and then add a current limit so that the fault current put out by the generator was capped at a certain level. So it might be 1.5 per unit initially, and then it rapidly decays to 1.1 per unit. And so you can put in those current values and then you can enforce them in the fault options window, which we'll cover next class. But that's what that's for. If now you can actually just model the type 3 and type 4 machines, so you don't need to use this going forward, but they leave it in there for backwards compatibility because as you can imagine, they modeled many of those inverters for years, and those may not have already been converted to type 3 or type 4 machines. So they leave that in there so that those models still work. The power flow regulation, you generally don't need to worry about. That's if you have the power flow module option, and it's used for power flow studies. Don't need to worry about that for our purposes where we're doing, just protection studies. So you can ignore that area. Current limits, power flow regulation. Yep, okay, covered all that. Once you model your generator, then you can edit or add new units, and you get this new window, the generating unit info window. Now you put in your MVA rating, your subtransient impedance, transient impedance, synchronous impedance, the negative sequence synchronous impedance, and the zero sequence synchronous impedance. So that's these values. One thing to note is generally the fault current from a generator is high right after the initial fault, and then it decays down to a synchronous output. And so the subtransient impedance is generally lower, and then the transient impedance is lower than that, and then the synchronous, higher than that, and then the synchronous impedance is higher than that, and that's why you have the inverse relationship between the fault current and the impedance. And the reason you need this is because Aspen has the ability to change which time frame you're looking at when you run your fault simulation. So say you want to find your maximum fault current, you would want to run your fault using the subtransient impedance of the generator because that's when the fault current is going to be highest. But if you've got like a time over current relay that is looking out into the system and it's got the generator behind it, but it's operating, say in 2 seconds or a second and a half or whatever, the amount of fault current put out by the generator is substantially lower in that synchronous range, in that 1 to 2 or 3 plus second time frame. And so if you assumed that the generator was going to put out the same amount of current it does during the subtransient period for that whole time, then you're going to get an inaccurate result when you try to figure out how long it's going to take that overcurrent element to operate. So again, you can do that in the fault options window. We'll cover that more next class, but that's why we have those different impedances. Aspen chose to just model them all the same for this generator, but generally these will be different. The neutral impedance in actual ohms, that's if the generator has a neutral impedance. You'd put that in here, just like you would for a transformer. The scheduled generation, that's used in the power flow simulation only, so you don't need to worry about that. And then the P and Q limits are actually not used in the software at all right now. They've put that in there and they may use it in the future, but right now it doesn't do anything, so you can ignore those. Where do we get the data for modeling the generator? So again, I've included some examples from a project I worked on. This is showing that current decrement for the generator. This would be the subtransient period, and then you've got the transient period, and then it goes down into the synchronous period. So that gives you an example of the curve I was talking about. And then this test report gave the subtransient reactance, the transient reactance, synchronous reactance, etc. And then it also gives you the time constants. So again, looks like the subtransient time constant is about 0.5 seconds. So anything over like 0.5 seconds, you're going to want to change your fault options to that synchronous impedance when you're running your fault, because if the relay is operating in 2 seconds, you're going to be in that synchronous time zone. So this is an example of where you might get the data for modeling your generator. Modeling type 3 wind plants, they call them wind plants, but and it generally is, but any doubly fed induction generator would be modeled using the type 3 wind plants. Similar to the synchronous generator, you do new type 3 wind plant, gives you one generator, and then you model the different number of units. You put in the MVA rating, the megawatt rating, because those can be different for wind turbines. Generally, they are. And then the megawatt generation, that's for the power flow simulation. And then you put in your converter current limits, and we'll talk about that. So these type 3 machines were introduced in 2021. Like I said, they're relatively new. It's been 5 years now, I guess, or 4 years. So they've been out there a little bit of time. But when you model your new type 3 wind plant, this is the window you get. You put in, again, the number of units, their MVA rating, the number of megawatts, and then the generation. You can generally ignore that. Then you've got the converter current limits, the rotor side limit, and the grid side limit, and whether or not it's crowbarred. This crowbarred option is to simulate faults that are very close to the terminals of the wind generator. So the fault current, Aspen One-Liner doesn't do a good job of modeling the amount of fault current that the wind turbines will put out if the fault is very close to the terminals of the wind turbine, because it can be up to 5 times the full load current. So they provided this option to kind of force that, and that makes it so that it puts out the right amount of fault current for faults right near the generator. You can think of a wind farm, and generally those turbines are really spread out, right? So you generally don't have to use that crowbarred option. I just wanted to point out that that's what it's for, because somebody might look at that and go, wait, what is this and do I need it? Generally, no. It's just if you wanted to figure out what your maximum fault current output for a wind turbine right at the terminals of the generator might be. This is important. In order to actually simulate the Type 3 wind plants, you need to go and enable that option in the fault options window and click the Simulate Type 3 wind plant. Generally, you'll just leave that on, but if you receive a model, the way that the one-liner models work is that the fault options actually save with the model. So somebody might have given you a model and then you add a Type 3 wind plant to it. You want to check your fault options window to make sure that you're going to simulate it. Otherwise, it's not going to put out any fault current. So you need to enable that. And the pre-fault voltage option must be set to from a linear network solution. So if you do assumed flat, you're not going to get your Type 3 and Type 4 generator fault current outputs. So just to keep that in mind. Once you've kind of set these up, you can click on the advanced settings. It'll open up this new window, and you've got other options here. In my experience, you can't get this data from the wind turbine manufacturers. They consider it proprietary generally, and they won't give it to you. So Aspen says in most cases you can just leave this at default. They worked with a company in Germany, the name escapes me right now, but they ran a bunch of simulations and determined what typical values are for different make and models of wind turbines and put in this information. So if you have it, great. If not, you can just leave it at default. So again, I've included an example of where you might get the information from a wind turbine generator manufacturer. Their data gives the MVA rating, the megawatt rating. Then it has the maximum short circuit current contribution. So this one had a value of 1.05 per unit continuous and 1.45 per unit peak. And so that would be talked about when modeling a current limited generator. That would be where you use those data, right? So A might be the short term or the maximum, and then this might be the continuous. And then you can in the fault options window enforce which current limit you want, so that your all of your current limited generators were putting out the same amount of fault current. Okay. Again, now that you can model Type 3 machines, you don't need to worry about that generally. But you might run into a model where somebody else had done that and want to know what it is. All right, converter interface resources. So these are your inverter power electronic generators, so solar farms and battery energy storage systems where there's no rotating equipment whatsoever, and the only fault current being provided is from the inverters, and it's based on the inverter logic. So those are Type 4 machines. They're similar to the Type 3 machines. You do new converter interfaced resource, gives you this this symbol here, and then you put in the number of units, the MVA rating for each of the inverters, and then the megawatt generation. Again, that's for the power flow option, and so you don't need to worry about that. You put in the maximum amount of current, and that's really what you need to focus on here. What's the maximum output of the inverter? And then if you click the advanced settings button, you can put in this data. This historically, when inverter technology was newer than it is now, they would only put out positive sequence current. We're starting to see more and more now that the inverters will also put out negative sequence current, which is important for protection because, as you'll learn about, I'm sure, in the distance protection classes, if you haven't already, the negative sequence current is important for determining polarity, whether or not the fault is ahead of you or behind you. I've recently run into the first project where I've actually had an inverter that put out negative sequence current, so that was cool. So I actually had to enter this this data. Just worked with the manufacturer to get that data from them. The resource shutdown, again, get it from the inverter manufacturer. You might have to work with them. It might be not be in their standard data sheet. You might have to reach out to the factory and find this information. I will say that I've run into issues with Aspen one-liner where my my inverter was not putting out enough fault current because I ran a three-phase fault on a bus nearby, and it would put out zero amps, and that was because this resource shutdown was set to, like say 0.5 per unit. And so if the voltage was less than 0.5 per unit, the inverter would shut down and it was saying, okay, we're not going to put out any fault current. So sometimes you have to play with this value if you don't know what it is from the equipment manufacturer. So just keep an eye out on that. You might run into that if you're doing faults around current interfaced resources. Okay, another example of a project I worked on where I received manufacturer data for an inverter and gave me, the subtransient, transient, synchronous impedances, and the short circuit current that was put out. So I used this data in order to model the current interface resource. Modeling shunts. Shunts, I think I covered this last class, but I don't remember for sure. But shunts are what Aspen one-liner refers to as capacitor and reactor banks, or I should say that the other way. So if you wanted to model a new capacitor here and you right-clicked on the bus and you said new and you want to model a capacitor bank, you're going to see that modeling a capacitor is not an option. It combines capacitors and reactors into just shunts because it's a shunt susceptance. Excuse me. So when you go to model your capacitor bank, what you're going to want to do is use this convert button. So it makes it really easy. All you have to do is enter the MVAR rating. And if it's a reactor, you put in a positive value. And if it's negative, if it's a capacitor, you put in a negative value. And so I can put in like, negative 20 and hit convert, and it'll automatically put in your susceptance for you. So yeah, just use that tool. And then if you happen to have like a resistor or whatever in series with it, you'd put in the megawatt value. Yeah, use the convert button. If the shunt is ungrounded, then G0 and B0 will be equal to 0. And if it's grounded, then the G0 and B0 will be equal to the B value, or the corresponding positive sequence value, I should say. The G and G0 values are only used for like dynamic VAR compensation units like DVARs, StatComs, SVCs, things like that. I've never modeled one. They're fairly rare, so I haven't had to worry about that. And you most likely won't either, but you may. So if you have to do that, I would just point you to the help files and have you reach out to Aspen on how to do that. But all right, now we're going to get into modeling relay groups. Let me check on my time here. 30 minutes, okay. Modeling relay groups. So in order to model a relay, you need to first model a relay group. So let's say we want to model the line protection from Minnesota to Montana here. What I'd first do is right click by that bus and then do new relay group. And it'll add this breaker looking device. And so that is now where you can model all of the relays that are looking at the current and voltage at that terminal of the line. Once you model your relay group, which again is that breaker looking symbol there, then you can model all the different types of relays and other protective elements like overcurrent relays, distance relays, fuses, reclosers, line differential relays, and voltage relays. So this is that new relay group or the relay group window I just showed. And then what you do is you go here and you add a relay. I can show you how to do that. You add a, let's say, new distance relay. DS stands for distance, so I can do a new phase distance relay. You select what type of relay it is. Let's say it's an SEL 411L. Okay, and then you set up your actual relay data. So I guess I don't want to do it that way, but that is how you would actually add the different relays to this group. The other cool thing here is if you've got digital relays, you can use this import function, and you can like select a GE setting file or an SEL accelerator file. And then if I browse to the one I stuck on my desktop for this purpose, it will actually read the settings file and it will tell you your firmware data, your relay part number, all this stuff. And then it will actually scan the settings file and identify the different types of protection that the relay has in it. And then you can hit OK, and it will actually import. So this is the phase distance element, and it will get all of these settings for you, and you can kind of see that if you had to open up the settings file and get the PT ratio, CT ratio, your zone 1 magnitude and angle, and the positive sequence magnitude and angle of the line, and your zone 1 reaches, and all this stuff, you can. There's obviously a risk of data entry errors, so you can use this import tool, and it makes it a lot faster. And then you can just say OK, 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 and OK. And now it's modeled each of those relay functions, the distance element, the phase time over current element, the ground instantaneous element, and then the ground time over current element, or the phase time over current element. This is the ground. Okay. So it modeled all of those different functions, which saves a lot of time. But I would caution you to make sure that you check this when you've imported it, and not for the accuracy of the import, because I'm confident all these values are the correct values from the settings file. I'm confident that Aspen made that set that correctly, but the relay may be doing things in logic that Aspen one-liner doesn't know. So as an example, you might have a pilot scheme, and the zone 2 element is used for a pot scheme, and so it doesn't directly trip the relay. You might have to set that as a signal only zone. Or you might have a zone 3 that's looking behind you that's part of that pilot scheme, and it's just doing a block, and you don't want to actually have the relay operate on the zone 3 element. You might have an overcurrent element that's set up for fault detection purposes, but doesn't trip the relay. So you don't want to model it as a relay in here without like disabling it or making it so it doesn't open the breaker in one liner, because you don't want it to assume that that overcurrent element will actually trip the breaker. So it might screw up your coordination if you do that. So that's one example. Another example is for this particular relay, there's a phase overcurrent element that it modeled here, but in logic, it's actually torque controlled, which means it's blocked by the zone 2 element. So in order for the phase time over current element to operate on its inverse time over current curve, the impedance to the fault also needs to be within that zone 2 reach of the phase distance relay. And so if you model it this way and put a fault that's outside the zone 2 reach of the relay, this might make it look like the relay would operate for that fault when it wouldn't, because it's not within that zone 2 reach. So Aspen has a way of accounting for that, because it's pretty traditional protection. They use that zone 2 supervision area on the phase distance relay. So now you can add your phase time over current curve. So what I would do if I imported this is I would have to delete this and then add that data to this zone 2 supervision area instead, so that I got a more accurate response of what will actually happen for a real world fault. Another thing here is that it modeled 2 ground overcurrent relays. Really, there's only one. So it took the instantaneous ground overcurrent element and modeled that here, but there's also a time overcurrent element, and you can actually model those together so that you don't have to add 2 relays to your model when you're doing your overcurrent coordination study. So I would delete the instantaneous element and add that data to the instantaneous element area of the ground time overcurrent element. So all that to say, import tool, great, very handy if you've got a digital relay, but don't just take that and run with it. You need to still understand what's going on in your relay and what it's doing, and model it correctly. All right, got off track there, but we're just talking about modeling relay groups right now. So you can add the relay manually, like I went over. You can import it, like I went over. You can copy and paste different relays. So let's say this is a relay and it's an existing setting, and I might want to make a change to it. And for coordination purposes, I may want to go back to how it's set today. I do this often, so I'll actually copy the existing settings and then paste, and now it gives you a little tilde in front. And so that's how I keep track of, like, this relay has had setting changes. So now I can make changes to this one, and I know that was the original setting. So then I can go back and compare and see how I changed things. And then you can disable, make it offline. So now the relay group is operating on this curve, because that's the one I want to study, but I still have this one here for historical purposes. You can also copy and paste complete relay groups. So if I right click in here and I do copy, I can paste that whole relay group. So now all of those relays are in here as well. The breaker operation section, this is if you want to include the breaker operate time in your operate time for that relay group. So if you look at the amount of time it takes for a breaker to open, it's both the relay response time plus the breaker operate time. If you're trying to calculate the overall operate time, you have to add the two together. When you just model the relay, the time that Aspen one-liner tells you it will take for the relay to operate is just the relay response time. But you can add in the breaker operation time, and now you can get that time adder, so you can get a more accurate coordination interval. Generally speaking, the coordination time interval accounts for the different operate times of the equipment. So that margin is kind of already built in there. So generally, I don't see this being added, but you can add it and get that more accurate response. The trip logic, generally you'll just keep that as the fastest device in the group, because what you want the breaker to simulate it's operating for is whatever relay is going to trip first. So whichever element is going to trip it first, that's the time you want for that breaker to open. And then maximum operations, that's for reclosing. So if you want to include the reclosing options that you have for a particular breaker, you can increase those operations, and then you can put in your reclosing intervals. I generally don't see that done for breakers, but you can do it. And then you can say whether the reclosing logic is always enabled, like if any element in this relay group would initiate reclosing. That's generally how it's done, but sometimes you might have like no reclosing for a transformer differential relay, just for example, because if the transformer differential relay operates, you don't want to reclose. Or there might be a particular element that, like a long time delayed ground element that you don't want to reclose for, or something like that. You'll see that when you actually look at the drop downs for these, the only option that you get is those. If you wanted to set up some of that logic for your particular study, you got to go to this protection logic and communication area, and now you can set that up. You can use and or gates. You can say that this is my, I don't know, POTT scheme, and do different and or gates to mimic some sort of protection logic scheme that you might have for your application. Generally, you don't need to worry about this. The pilot comm channels, again, I generally don't worry about this, but you can add a, it's actually got some default here, custom. So you can actually add like a pot scheme or a DCB scheme, and then you can say that that's part of a pilot communications channel. Yeah, it's not listed here because we haven't set up the logic scheme yet, but if you do that, then you can set it up as a pilot comm channel, and you can actually make it so that the two ends of the line interact even in Aspen one-liner. You can also set up coordination pairs in this area, which just makes your coordination studies more efficient. So let's say, just because we're right here, there's a fault on the high side of this transformer. We would want this breaker to open first to isolate that transformer, and not have like this terminal and this terminal trip for that fault. But if this breaker didn't open for some reason, maybe the relay didn't operate, or the breaker failed, then you'd want these breakers to open to isolate that fault. So they're one step back from where the fault is, and so they're backing up that breaker. So you can set that in here. You can say that this relay group backs up the terminal from Montana to Montana medium voltage bus A, Montana to Montana medium voltage bus A, boom. And now later on, when you're doing your coordination study, there's actually ways to like select which relays you add to the plot based on whether or not they back it up. You can also do more advanced functions using scripts to kind of automate that process. You can say, okay, there's a fault here, check the coordination with all devices that back up this relay group, and it'll automatically generate those plots. I haven't messed with that a lot. I have seen it. I have some clients that are starting to move in this direction and automate these functions more and more. So that's where you do that. I guess just know it's out there. I haven't really messed with it. I probably should. Might make things more efficient for me, but I have to put in the time to figure it out. Okay, we talked about logic schemes, pilot comm schemes, coordination pairs, and none of this is necessary, just nice to have features in some applications. All right. Now we'll talk about how to model overcurrent relays. Overcurrent relays, just like the name implies, they're relays designed to trip when the current is greater than desired. You've got the pickup, the curve, the tap unit. The tap unit is not necessary in older electromechanical units. They would change the pickup by actually changing it was like a screw tapped into a hole, and you remove that and put it into a different tap and screw it in, and that's what the new pickup is. This doesn't actually impact the pickup in the relay. It's just there for documentation purposes. So you generally don't need to worry about that. It'll work without it. The time dial, the time adder, and the time multiplier, and then whether or not the relay has directional control. So to just go over each of these briefly, the pickup is the value at which, if the current is higher than that value, the relay will start to operate. Okay. If it's an instantaneous element, if it gets above that, it's just going to trip. If it's a time over current element, it's going to operate on the time over current curve, and that'll be based on the multiples of the pickup that the measured current is. And we'll talk more about that when we look at coordination. The curve adjusts the curve shape of the overcurrent element, whether it's inverse, very inverse, extremely inverse, moderately inverse, or just linear. Lots of different curve shapes. Tap unit, like I talked about. The time dial, when you have your time over current curve, I don't know if this is mirrored or not, if I'm pointing in the right direction, but when you have your time over current curve, when you adjust the pickup, you are basically just moving that curve shape to the left and right. So the x-axis is current and the y-axis is time. And so if you change the pickup, you're changing where that curve is in relation to the current. So let's say you increase the pickup, it will require more current for the relay to operate. If you decrease it, it'll go the other way. The time dial is kind of the same thing for the y-axis. So if you increase the time dial, it will shift your curve up, and if you decrease it, it'll shift your curve down. And so that's how you can that's the most intuitive way I can try to explain how that impacts where the curve lines up on your curve plot when you're doing your overcurrent coordination. The time adder is if you wanted to add a definite time on top of your curve. You generally don't see that done, and that would adjust the curve shape a little bit too. Generally don't have to worry about that. The time multiplier is same thing, generally not used, but that would change the curve shape a little bit if you have that option and choose to use it. The directional control, this is important. You will use this, and you'll use it often. You need to make sure that you do that if it's a directional element. If you don't set that up, then the relay group will look like it operates for faults behind you, okay, when it otherwise wouldn't. So when you do like a stepped event analysis, it might show that this relay group opens for a fault over here at some point, even though it shouldn't, because the relay is directional and it's only going to operate for faults in the forward direction. So you definitely want to enable that if your relay is directional. And then when you set that up, you have to look at your particular relay, see how it's polarized, whether it's zero sequence voltage, zero sequence current, negative sequence current, And once you select that, then you can put in the operating characteristics from the settings file. And then Aspen one-liner will correctly mimic the logic in the relay and tell you whether or not it's going to operate for a fault at a particular location with whatever impedes. One other thing to note about that is the relay group, the forward direction is towards the line or transformer, and the reverse direction is towards the bus. And that's intuitive in most situations. But sometimes you might have a relay that has a CT that's wired with the reverse polarity. So for that relay, forward is towards the bus and reverse is towards the line. And if you just put in all of the settings exactly like they are in the relay, you will get an incorrect response from Aspen one-liner because it will say that forward is towards the line because it doesn't know that the CT is wired in with a negative polarity or reverse polarity. So be cognizant of that. I have run into that in projects and studies. There have been instances where I had to split this line, 0.01% of the line length. It put it at the other end. I guess I can do 99.9% of the line length so that there's a very small impedance here. And then on this side, I can do a new relay group. And now I can model my relay here so that it's looking that way. So I've had to do that. Not very common. Just be aware that sometimes you have to kind of trick the software so that when you put in the settings that you have, that you'll get the right response. When you model your overcurrent relay, this is an overcurrent relay. When you go to select your curve, you'll get this drop-down menu, and what you want to do is select from library, and then it'll open up this big library that has a ton of different manufacturer curves. So you can select your Cooper curve. In this data window, they'll say where they got the information from, what your current range is, time dial range, and they've got the catalog curve number 6. So they generally publish that data. It's a lot of curves to say where they got the information from. If it's published, they'll also give you the equation for that time over current element. So, which is kind of cool. I've had to go get that before and calculate a time for testing purposes, for instance, and the curve equation is right in there. You can, if for some reason you're adding a relay and you can't find the curve for your relay, you can add your own. I'm not going to really cover that. I think I did cover how to do it using the overcurrent curve editor. And then you can set up your own. I'm not going to go over that. It's not very common. Usually they have the curve that you need, but you can add one if you need to. And I have had to do it in the past, but it's not typical. All right, modeling distance relays. Distance relays are generally meant to operate when the impedance measured by the relay is less than desired. And I'm sure that if and when you go over distance protection, you'll cover all of this. So I don't want to waste our time going over all those details. But when you model your distance relay, you put in the PT ratio, CT ratio, and then the settings that relay has. So this is a 311L relay or 311P relay, P for phase or G for ground. But it's a SEL 311 relay. And then you just get these settings right from the settings file. What else did I want to talk about here that's specific to Aspen one-liner? So, no, I think you're going to cover all this in distance protection. I don't want I don't want to waste our time on this. Okay, and I talked about the zone 2 supervision. So generally, you just find the data for your particular relay, put it in here, and it'll work. There's nothing nothing overly fancy as to model and distance relays that we haven't already discussed. I guess I could talk about this signal only zone. So if you have an element that's part of a pilot scheme, like I talked about before, and you don't want the relay to show that it's operating on that zone, you put it in as a signal only zone. So if you've got like a distance element as part of a pilot scheme, you'd say that it's a signal only so that it doesn't say that the relay is going to operate as soon as you see a fault within the zone 2 reach. So if it's zone 2, you put in a 2. You can do 2, 3 to say both the zone 2 and the zone 3 are signal only zones, but that's how you do that and correctly model those non-tripping zones. I mean, they do trip, but they're part of the pilot scheme, and you don't want to include them as part of your operate time for the relay if you're checking distance coordination or overcurrent coordination. Okay, you can also model fuses, which are most commonly used to protect the high side of power transformers. I believe that Leo went over distribution protection, so I'm sure he covered this, and we're also going to cover it more when we talk about transformer protection in a few weeks. So I don't want to go into all the details about how fusing works. I just want to cover some of those specifics as it relates to Aspen one-liner. So generally what you need, you just give it a name, then you do the curve selection, just like we showed with an overcurrent relay. When you model a fuse, I've got one modeled here somewhere, right here. Okay, you do this drop-down menu, and now you can see, again, all the different manufacturers of fuses, and they've got a ton of them in here. So I chose a SNC very slow speed fuse, and this was a 132 kV fuse. So I found the TCC, the time coordination curve number, and selected the voltage range. Okay, and then so it's a curve 176-19. That's where this comes from, the 176-19. And then the last 3 digits are the continuous current rating of the fuse. So it's a 100 amp fuse. Pretty simple to model as long as you can find the curve number for your particular fuse. The current divider entry is if you have multiple fuses in parallel. So say the maximum curve rating, maximum continuous current rating you can get for a particular fuse is 100 amps, but you want a 200 amp fuse with that curve shape, then you can put 2 in parallel, and now half the current goes through each fuse, and so you've effectively doubled the continuous current rating, but you're still going to operate on the same curve. So that's where you'd use the current divider. So if you have 2 fuses in parallel, you'd put a 2 here. Generally, you just leave it at 1 because you only have 1 fuse per phase. The minimum melt multiplier, this is important. I'm sure Leo talked about fuse saving schemes, and we're going to talk about them when we talk about transformer protection. But if you have that multiplier that you need to account for when you have fuse preheating, this is where you'd apply it on the fuse. So you'd only do that for specific instances, checking coordination between like a recloser and a fuse to account for that preheating. And again, we'll talk about it more when we talk about transformer protection. So that's where you put it in. The installed on the branch terminal, that's generally where you'll put it. You can see that there's only that option, so you don't need to worry about that. Compute time using, whether you want to use the minimum melt or the total clear. So when you're, if I show this over this fuse curve. The minimum melt curve is the bottom of this fuse curve, and then the total clear is the top. And basically the inside here, this hashed area, is the area, the amount of time, the difference in the amount of time where this fuse could blow. So it can actually blow at any time between these two curves. So generally manufacturers will publish a minimum melt. That's the minimum amount of time it's going to take for that fuse to blow. And then a total clear, which is the maximum amount of time for that amount of current that it will take the fuse to blow. You can, I mean, you can understand that the fuses are not very precise devices. So there's a range there. And so that's how they define that, the minimum melt and the total clear time. The reason you've got that option is if you're coordinating with a curve that's down here and you want to make sure that the fuse is always going to be slower than, say, a downstream recloser, you want to coordinate against the minimum melt time. Okay, and you want to make sure that your margin is between the minimum amount of time it could take for the fuse to blow and your recloser operate time. Okay, and inversely, if you are coordinating with a recloser that's upstream and you're the downstream fuse, you want to make sure that the fuse always blows before the recloser operates. So you want to coordinate against that total clear time, right? Because that'll give you that minimum amount of margin between the two curves. So if I run a fault here, say at this bus, it's 3 line to ground, okay, and then I show my curve. So this is my fault current. Again, we'll talk about this more in next class. I just want to demonstrate. Right now, I've selected minimum melt. So the minimum melt time for this fault is 1.143 seconds. And then if I change this to the total clear, now I get the 1.452 seconds. So that's that difference. So when you're, like if I add I can't touch that button, add a time difference slider and to give me the difference between two curves, it's going to select the time that's shown here. So if I change that back, now it's going to compare everything to the minimum melt time. Okay, the next type of device we're going to talk about modeling is a recloser. Reclosers are similar to breakers. They're smaller and cheaper and generally have lower ratings for continuous and interrupting ratings than breakers, but they're very common for distribution protection. And they kind of have a unique or typical setup where they have fast and slow curves as part of that fuse saving scheme that we're going to talk about and that Leo, I'm sure, has talked about as well. And so when you model a recloser, they give you all of that set up in the recloser. So let's see here. Okay, we'll just go from top to bottom, I guess. Reclosing intervals. 222 is very common in my experience, 2 seconds. So this is where you put in the reclosing intervals. This is good to enter and keep track of because the number of shots and the interval between shots affects the multiplier that you'll use, the correction factor for coordinating between fuses and reclosers to account for preheating of fuses. So the software doesn't use this to adjust those times, but you kind of want to enter it so that if you have to go back and figure out what your K factor is later, you've got the reclosing intervals already in there. So you can put that in. And then same thing with the total number of operations to lockout. So there's 3 reclose attempts. So this recloser is going to operate a total of 4 times. It's going to operate the first time, reclose once, operate again, reclose a second time, operate again, and then reclose a third time and operate for a 4th and final time. So 4 operations to lock out. That's why sometimes this can be confusing, or maybe it confuses me unnecessarily. But when I first started doing this, it was like, oh, I got 3 operations. No, you have 3 reclose attempts. You have 4 operations. So the number of reclose attempts will be 1 fewer than the total operations to lock out. And then also the number of fast operations. Again, software doesn't really use these for anything, but you want to put them in there so that you can select the correct K factor when you do your coordination. You select the curves for your fast and slow curves, and it gives you both the phase and ground, and they're combined. Back when we were working with the relay groups, we modeled the phase overcurrent and the ground overcurrent separately. When you model a recloser, you do it all in the same recloser, because that's generally how reclosers are set up. And then similar to the fuses, when this little bubble here, when you select this bubble, the time that it tells you that it will take for the recloser to operate is based on the fast curve. Or if you select this one, it'll be based on the slow curve. So you change these, again, depending on whether the recloser is downstream or upstream of the fault, and which one is going to be the worst case for your coordination time interval. So when you model both of these curves in here, it'll have the curves. It's just selecting which one the relay is going to operate on when you run your fault. Okay. Line current differential relays you can model in Aspen one-liner. I've never done this. Generally, you kind of do that logic separately. You can figure out what your internal fault current is going to be for a fault on the line, and then what your external fault current is going to be for close-in faults on either side, and you can figure out what you need to set your differential pickups to based on that. And there's really not a need to model the line current differential relay for coordination purposes, because if the fault's on the line, the differential is going to operate. And if the fault's not on the line, the differential is not going to operate. So there's nothing really to coordinate with there. You can kind of just take credit for the fact that you have a line current differential scheme when you run your coordination study. But you can model it and put it in here. I'm not going to go over that in detail because it's not common, at least in my experience. Same thing with voltage relays. Generally, you don't model those because you don't need to worry about it for coordination purposes, but you can model them. The only thing that is really worth noting here is the operate on voltage. You're going to want to make sure that you select that when you model the voltage relay. So you can, let's add a voltage relay. You can say whether it's operating on a phase to neutral value, or a positive sequence voltage value, negative sequence, or an individual phase or phase to phase. So you want to make sure you select that. And then it's pretty straightforward. You put in your PT ratio, and usually it's a definite time. I don't think I've ever seen a case where a voltage element operated on an inverse time curve, but you can select it if you want, if you have an application where that's the case. And then you put in your pickup and delay, and away you go. The signal only is if it's not used for tripping. And then if you have an instantaneous element also, and then you've got the over voltage element and under voltage element that you can model for each type of voltage relay. All right, running faults. Wow, okay, I did this faster than I expected, which is good because usually I go way over. I was trying to be faster, and apparently I was. So I would open it up for questions, but obviously this is a recording, so I can't do that. But if there are any questions, feel free to reach out. Uh, and yeah, I guess that's all I want to say. So next class, we'll start with running faults. We'll first set up our fault options window, and so that we make sure that we're running the faults the way that we want. And then we'll go over how to run different kind of faults and check different types of coordination. Okay, I will give you 5 minutes back. Thank you so much. We'll talk to you next week.